So before consolidation, we can sort of indicate weak memories in the cortex using sort of black and white, and it's kind of faint here. We have the concept of an amoeba, we know what the word is and maybe what they look like, etc. So that's before consolidation. After consolidation, we have stronger cortical memory traces, and they are linked together, and so this is part of our semantic memory at this point. Now, if somebody asks us this question, do you remember learning about how amoeba eat? Again, the question is a cue, and it will reactivate some of the hippocampal memory trace, and then pattern completion will activate the whole hippocampal memory trace, and then that will activate all of the cortical memory traces. And if we can call up lots of detail and the context of the learning experience, the circumstances of learning, then we would be having an episodic retrieval. And I'm indicating here that it's episodic because we're remembering sort of the circumstances of learning, like the feel of the microscope. On the other hand, if somebody asked us, what do you know about amoeba? Here again, the same kind of cue is going to reactivate a memory trace, but it may well be that we don't activate all of the details of the learning experience. We might just activate the knowledge. We might just reactivate the memory traces associated with what an amoeba looks like and what the sound of the word amoeba is and some basic facts, but we're not reliving the experience. And this we're going to call semantic retrieval. And I've indicated the difference here is that we're not sort of reliving the feel of having our hands on the microscope. That's not being reactivated. Whereas in episodic retrieval, it's a more sort of detailed, context-rich, a more sort of reliving of the learning event, whereas semantic retrieval, we're just getting at the information, what was learned the day before. But importantly, early on, the hippocampus is necessary for both kinds of retrieval. Whether we're doing episodic retrieval or semantic retrieval, the hippocampus is required. Remember, the cortical memory traces are weak, so we need that index in the hippocampus to help to activate the cortical memory traces to retrieve the memory. But after successful system consolidation, we will have stored semantic memories in our cortex, and even if at some later time our hippocampus is removed, we can still access semantic memories stored in the cortex. Now let's tackle what the hippocampus does with multiple events. Now, scientists have discovered that the hippocampus is very good at doing a few important things for memory processing. And the idea is the hippocampus can make separate memory traces for different learning events. Here we have the memory trace for event 1, receiving inputs from the cortical regions that were processing event number 1. And here we have the memory trace for event number 2, receiving inputs from the cortical areas that were processing event number 2. And the hippocampus can make distinct memory traces for events 1 and 2. If events 1 and 2 are separated in time, then events 1 and 2 get encoded by non-overlapping populations of neurons, even if event 1 and 2 share characteristics. Hippocampal circuitry is well suited for what psychologists call pattern separation, the ability of the circuitry to generate different outputs for similar inputs. And this allows the hippocampus to make unique memory traces for ongoing events. So when events 1 and 2 are separated in time, distinct memory traces are formed. But what happens when events 1 and 2 are close in time? And here we're going to use our brain to paint the picture of this kind of process. So we're going to have the brain processing event 1. We'll have some pattern of cortical activity, and these regions of the cortex will send information down into the hippocampus, and a set of hippocampal cells will be allocated to forming a memory trace of the event. Number 1. It's the most excitable hippocampal neurons that are allocated to the memory trace of event 1. And so this is a recent discovery, that it may be that the levels of excitation of hippocampal neurons is influencing whether they will be used at that moment to form a memory trace of the event. Now, because these hippocampal neurons have just been activated in forming the memory trace for event 1, they remain in an excited state. And this means they're going to be preferentially allocated for the next event as well. So activated hippocampal neurons sustain their elevated excitability and so are more likely to be allocated to event number 2. So along comes event number 2, and notice the different pattern of cortical activity because it is a different learning event. Let's just confirm that. Event 1, Event 2, Event 1, Event 2. But notice down in the hippocampus, the hippocampal memory trace shows a lot of overlap. These 3 neurons were also in the memory trace for Event 1. It's the addition of this 4th neuron that is included in the memory trace for Event 2. So many of the same hippocampal neurons are allocated to the memory trace of event number 2. In addition, we know these hippocampal memory traces are linked to the cortical memory traces, and in this case we have 2 sets of cortical memory traces. The traces for event 1 and 2. So the hippocampal memory trace now will be linked to both sets of memory traces in the cortex. Should we get a retrieval cue for event number 1, you'll recall the cortical memory trace here for event number 1 will reactivate part of the memory trace in the hippocampus, and then we get pattern completion. The entire hippocampal memory trace gets activated, and then that activation will send signals to the cortex to reactivate both memory traces in the cortex. This means that retrieving the memory for event 1 will tend to lead to retrieving the memory for event 2. The memory traces are linked. And again, system consolidation comes along. And recall that the process is such that the hippocampal memory traces get reactivated and then they're used to strengthen the cortical memory traces. Well, since the memory traces for event 1 or 2 are activated together, the conditions for neuroplasticity are satisfied in the cortex, so the memory traces for event 1 and 2 will tend to be linked together in the cortex. And this then is how system consolidation can begin to build networks of knowledge. Here, the memory trace for event 1 and 2 will be linked together in our cortical system. Now, linking the memories for event 1 and 2 makes good sense because they occurred sequentially. It may be that event 1 caused event 2, or the 2 events are related in some other way. Later on, thinking of event 1 will likely cause the retrieval of event 2. And that's really a useful feature of a memory system if event 1 and 2 are related in important ways. And so this is how we can build up our semantic memory. Linking memory traces is how we build our network. So system consolidation transforms an episodic learning episode into semantic memory. Communication between the hippocampus and the cortex strengthens and integrates the new memory into the cortical network of prior knowledge. So episodes provide the content for semantic memory. And we're going to loosely associate episodic memory with the hippocampal system and semantic memory with the cerebral cortex. Now, why do this system consolidation? Well, this will be one of our first reasons for why we're consolidating memories. Consolidation allows newly learned information to be integrated into semantic memory. So when we go through life and we have learning episodes, the stuff that we're learning will be integrated into our already existing knowledge of the world, our semantic memory. And so simplistically, the icon for that would be sort of the episodic memories are being transformed, or they're being sort of stored in semantic memory. And that's what system consolidation does. So system consolidation integrates new information. So on subsequent days, I might learn that amoeba are single-celled. Maybe I didn't know that the first learning episode, but I learned it the second day. Well, system consolidation can integrate that fact into the network of knowledge in my semantic memory, and I can build this network of knowledge and keep adding things to it. In fact, scientists suspect that the richer that our semantic memory system is, the easier it is to learn more. So knowing more things makes future learning more efficient. So if we have a lot of knowledge stored in our semantic memory, it makes it easier to insert new knowledge into that network. Again, if we're doing episodic retrieval, we are retrieving lots of details in the context of the circumstances of learning. Oftentimes we forget the circumstances of learning. Nevertheless, if system consolidation was successful, we're going to have lots of information stored in our cortex that can be retrieved by other brain systems. Frontal lobe brain systems can retrieve that even without a hippocampus. Now, in the school setting, then, we want to effectively consolidate episodic learning into long-lasting semantic memories. Being educated means having lots of information in semantic memory. We need not remember all the details of our learning circumstances to build a rich repository of semantic knowledge.